Hey everyone, welcome back. So today we're going to be solving another problem. Uh, so I'm going to be doing a series on trees, and I'm going to be solving problems from various resources. Uh, One is from Leetcode, another one is from Striver, and wherever I find the questions which are interesting. So today's question is lowest common ancestor of a binary tree, and there's a medium question. I'll be solving the question in Java, but the entire logic, the entire function, it is language independent. You can code it in any language that you want, but I'll be coding it in Java. Okay, so let's get started. So the question says that given a binary tree and then you're given two nodes with you, that is P and Q, you need to find a least common ancestor between those two nodes. Okay. For example, let's say that the node that is given to you is, let's say 5, and the second node that's given to you is, let's take 0. Okay. Now, the lowest common ancestor for 5 and 0 is ideally 3, right? Because if you see 5 over here, the ancestor above that, if you don't know what an ancestor is basically whenever you have an ancestor for a node, it's basically whenever you go up, whatever you find on the top, that's the parent node, right? That is your ancestor, right? So for example, if you consider only this tree, the ancestor for 2 is 5, right? Yeah. So now our task is to figure out the lowest common ancestor. Now given that our P is 5 and then Q is 0, our lowest common ancestor is what? It's 3, right? Yeah, because the ancestor of 5 is 3 and the ancestor of 0 is ideally 3 when the path is like this, right? So your answer would be 3. So our point is to determine what is the lowest common ancestor. Okay. Now if I give you another one, let's take 4 and 6. Okay, let's make our P 4 and Q 6. P4 and Q6. Okay, now what is the ancestor? What are the ancestors that I can get? Can I say that can I say that for 6 and 7, 3 also can be my ancestor, right? It makes sense because 3 is a common ancestor between 6 and 7. I can say that. But is this the lowest common ancestor? No, right? Because you have 5 over here. 5 is also a common ancestor for 6 and 7, which comes before 3. If when you go from bottom to top, your 5 comes before 3, right? So your answer would be 5. Okay. So I hope you understood the question. Let's get into the intuition of this problem. Okay. Now there are actually two ways of solving it that I figured out. The first way is that let's actually take the example mentioned. Okay, these examples are easy. Let me take a more tedious example. 6, and then let me take 4. Q equals to 4. Okay. Now there are two approaches of solving this problem. The first approach is, when you think about it, what is the first approach? So when do you find an ancestor for a given node? You find the ancestor of a given node when you're traversing to that node. But that what I mean is, let's take ancestor of 4. How do you get all the ancestors of 4? When you're going from 3 to 4 is when you get the ancestors of 4, right? Makes sense? So whenever you take 4, this would all of this would be ancestor, right? Similarly for 6, what would be ancestor? The path that you take from the root node till the required node would be all the nodes on that can be ancestor, right? So for this one, I can say that this is the path that I'm taking, right? I can't take any other path. This is the path that I'll be taking. So I can say that this is the ancestor for this. 5 and 3 are the ancestors for 6, right? So now when I find the path for, let's say, 6, I find the path as 3, 5 and 6, right? And for 4, what is the path? It is 3, 5 2 and 4. So if I have path for both of them, can I not say what my ancestor would be? I can, right? When I'm coming from 3, I'm going to 4 like this, right? When I'm going to 6, I'm going like this. So there is a common node, which is our ancestor, right? So once I find out all my path to 6 and to 4, I can easily figure out what is the ancestor, what is the least common ancestor, right? What will it be? It'll be nothing but, see, 3 is our ancestor, but 3 is a common ancestor, but is 3 our answer? No, we have already discussed this, because 3 is not the least common ancestor. So what I'll do is, I will update my answer with 3. Okay, my answer will be 3 currently, because both of them are equal, right? Then I go to 5. I see that 5 and 5 are also equal, which means that even this can be my ancestor, and this is also closer to my P and Q compared to my previous answer, right? So I can update this. I'll update this. Now I'll go to this. These are not common, so now it will come out. Now I found out my ancestor, right? Now 5 is our answer. Let's see, is 5 our answer? Okay. For this is a path, and for this is the path, right? Yes. So 5 is our answer. Okay, this is one way to do it. How would you do this? This is very simple. All you'll have to do is from the root node, you'll have to keep going, okay, and then you'll have a list with you. In that list, what you would do is you will keep appending the values, okay. You'll keep appending the values, and then you'll keep appending the values on the list. And when you find the root equals to your P, okay, then what you do is you return that value, and then you keep returning it back. Now you can ask me, hey Siddharth, if I'm going towards the left, let's take any order traversal. Let's take pre-order, in order, or post-order. For now, let me consider pre-order. Okay, so what I'll be doing is I'll be checking if the root node will be equal to my P. Okay, no, not P, let's do Q. Okay, I'll be checking if my root node will be equal to Q. Okay, it's not, so I'll go towards the left. Right, now again it's not, so I'll go towards the left. Now I've reached the null node, right? This is my null. Now you can ask me, hey Siddharth, if my 4 is over here, okay, and I'm traveling through this, let's say I come back to this also, wouldn't my list have 6 in it? That is where your trick is. Whenever you come to a leaf node, right, or whenever you come to your last node, okay, if you still have not found the root, then all you'll have to do is you return it, and then you remove it from your list. You just remove it from your list. So now ideally your list would have had 3, 5, 6, right? Would have had 3, 5, 6. Now what I'm saying is I'll return it back over here, then I'll just remove it from my list. I'll remove this. I'll remove 6. So now my path is 3, 5. Now I'll go to 2 again. I'll go to 2. Now I'll add 2. Okay. Now I'll go to 7. I've gone to 7. Is this my path? No, it's not, because I've still not found the root. So I'll remove this. So what I'll do is I'll remove this. Then what I'll do is I'll come back. I'll go to 4. Right, now I've gotten 4. Now I've gotten my answer as 3, 5, 2, 4, which is the path. If you see 3, 5, 2, 4 is the path, and I've gotten the answer, I can just return it back. Or you can do one thing, you can set your list as a global variable, and then you can do the recursion and keep updating the list Okay, this is a fairly simple solution, but you'll have to perform it for 6, and also you'll have to perform it for 4. Then you'll have to iterate through the array, and then you'll have to do the computation again to find the common ancestor, right? So your finding value of P would take n, finding value of Q would take n, then your your computation to find the least common value would also take a time complexity of n, right? Ideally this is n, but this complexity is n, this solution is good enough, but there is a way where we can optimize this, right? There is a way we can write this shorter. Okay, now uh, now let's do one thing. Okay, let's take the same example again. 3 5 6 2 1 0 8 7 and 4, right? Okay, now let's look at a better approach. Again, it is a recursive approach. One thing I forgot to mention initially is that this is obvious now. We this solution, solution 1 is using DFS, where I'll be using pre-order. Okay, now let's go to solution 2. This will be our solution 2. What will we do in our solution 2? Let's look at it. Okay, what I'm saying is that I'll take P as 5 and Q as 4. No, let me take P as 6 and Q as 4. Now what I'm saying is I'll apply the same thing again. I'll apply pre-order again. Okay, what I'll do is I'll go here. How does pre-order work? If you guys don't know, pre-order is basically node left and right. You'll access the node first, you'll do the operation on node, then you'll go towards the left, then you'll go towards the right. Okay, so now I'll go towards the left. Okay, now I'll check. Okay, before going towards the left, I'll have to validate, right? What I'm going to check is my 3 equal to P? No, it's not. Okay, is my 3 equal to Q? No, it's not. So I'll go here. Okay, 5. Is my 5 equal to P? No, it's not. Is my 5 equal to Q? No, it's not. I'll go towards the left. I found 6. Okay, is my 6 equal to P? Yes, it is. So in that case, what do I have to do? I'll have to return that value. So let me return back 6. Perfect. Okay, now let me go towards the right. That is right of 5. That is 2. Is my 2 equal to P or Q? I mean, I'll be checking it every time, because again, if you see the constraints over here, your node dot value is always unique. Okay, so you're not going to have two values in the same tree, right? If you have two values in the same tree, ideally this solution would not apply, but you would not have two values in the same tree. Your values would be unique, right? So now whenever it goes to 2, I'm checking if 2, I've already gotten my P, but I'll be in my code, I'll be checking it, right? I'll be checking if it's equal to P or if it's equal to Q. No, it's not. So then I'll go towards the left. Okay, is it equal to P? No, it's not. Is it equal to Q? No, it's not, right? So what will I return? What do I have to return? Let me do one thing. Let me return null. Instead of returning anything, let me return null. Null. This is X and this is X. Let me just return null, right? Ideally, how would it return null? Basically, it will go to 7, and then from 7 it'll check left, which is null, so it will return back null, and then it'll check right, which is also null. It'll return back null, so this will also return back null, right? Now my n is done, L is done for this particular subtree is what I'm talking about. Now what I'll do is I'll go towards the right. 4. Is my 4 equal to P or Q? Yes, it is. It is equal to Q. So what will I do? I'll return 4. Just like over here, how we return 6, I'm returning 4. Nothing. It's very simple. Okay. Now I return 4. Why am I returning 4? Why am I returning null? We'll understand over here. The reason is that whenever you're checking, right, in this particular root, in this particular node, whenever you're checking left and right, whenever you're checking left and right, if left is null, over here, I can just return right. Because if you see, right is the value that I found, I can just return right. Right? Now, else, if right is null, can I not just return left? In this scenario, we couldn't do it because we have found the value. But let's just say that our 4 was over here instead of over here. In that case, this would return 4, this would return null. Now, I want the, what do I want? I want the lowest common ancestor, right? So when you have 4 in null, can I not just return the value which is not null? I can, right? So I'll be returning, when right is null, I'll be returning left. Else what is the case? If left is null is covered, left is null is covered, right is null is covered. What is the other case? Other case is that basically both of them are not null, which means that there is some value to it. I'm coming to that point. Okay. Now I have returned null. So according to our case, when left is null, I'll be returning right. So what I'll do is I'll return 4. Yes. So now we have come to this final else condition. This particular else condition. Here what am I doing? Nothing. Whenever left is not null and even right is not null. Right? When left is not null and even right is not null, what do I have to return? Which means that in my recursive call, somewhere left value has been returned and even right value has been returned. I can see that, right? I'm only returning the value when the value is equal to P or Q, or else I'm not returning. I'm just returning null. So whenever this left value or right value is not equal to null, I know for a fact somewhere in my recursive function, I got my left and right value. Right? So whenever I get it, whenever both of them are not null, can I not just return my root? Makes sense, right? Now I've gotten 6 and 4. Now this condition will become true. So what will I do? I'll return 5. Okay. Now for this particular node, n is done, L is done. It'll go towards the right. That is 1. Right? It will right. I'll check. Is my 1 equal to P or Q? No, it's not. Then it'll go towards the left. Is it equal to P or Q? No, it's not. This value will return null. Then it'll go towards the right. This value will return null. This value will return null. Right? What will this return? This will also return null. This will also return null. When this returns null, what case is happening? When right is null, I'm returning left. When right is null, so I'll be returning left. So what will I do? I'll just return 5. This 5 will be returned to my parent call. Is 5 my answer? Yes, it is. The last scenario also, what did we find? We found out that 5 is our answer. In our recursive call also, what did we find? We found out 5 is our answer. Right? The solution is very simple. It just takes a bit of time to understand it. But once you trace it, just like this, just like how I've traced over here, if you trace it, you'll be able to understand it clearly. Okay? So let me write the code for it now. I'll be writing the code in Java, but okay, this concept is similar to any other language. Okay? So let us forget about the return type. Let's forget about the return type for now. Let's forget about what we're gonna call from the parent function. Let's forget that. Let's just write our recursive function. Okay, let me write public. I'm gonna forget this thing now. I'm gonna call it recursion to keep it simple, and then I'm gonna take in the tree node. Right? Oops, sorry. Okay. Now, what is our base case? What is our base case? It is nothing but whenever my left value is null and the right value is null, I'll be returning null. Right? That is my base case. So if root equals to null, so what I'll do is I'll return null. I won't just return anything, I'll return null. I'll tell you why. I've already discussed why, but I'll tell you this, you'll understand this much better when I give the return type for this particular call. Okay. Now, I'm doing pre-order, so I'll have to check. Right? Okay. There's one more param I need to take in. Pre-node, P, and then pre-node Q, right? So what am I checking? I'm checking if root equals to P. If it is equal, I'm gonna return P. I'm checking if root equals to Q. If it's equal, I'm returning Q. Return Q. Make sense? It's not. If it's not, what do we do? We perform the pre-order. That is nothing but LNR, right? That's exactly what we're gonna do. What we're gonna do is we're gonna call recursion of root dot left comma P comma Q, right? And then recursion of root dot right comma P comma Q, right? Makes sense. Now after we did that, after we went to the left, and then after we went to the right, what do? We check. That's exactly what we did. We check, right? We check over here, right? If you know what, I'm gonna have something called as tree node left equals to, okay, and here also tree node right equals to, okay. If left equals to null, I'm gonna return right. If right equals to null, then what I'm gonna do is I'm gonna return left, right? Else, what I'm gonna return? I'm gonna return root, right? Makes sense? Okay. Now what will be our return type? What do I have to return? I have to return a tree node. If you see, this is the return type over here. So our return type would be tree node. Now, if let's just say that there is no, let's just say that our node itself is null. Like we don't even have a tree. Let's consider that scenario, right? When we don't have a tree, it's good for me to say that I can return null, right? It's making sense now. The reason I'm returning null, that is one of the reason, and the second main reason is because if I'm not found the value, all I'm doing is I'm returning null so that I can compare this left and right value. So I can compare left and right value. Okay, perfect. So let's run this code now. Sorry, before we run this code, we need to call it, right? I always forget. So let me call recursion of, let me actually return it. Return recursion of root, comma, P, comma, Q. P, comma, Q. Perfect. Let's try to run this and let's see how it works. Perfect. Let's submit it. Perfect. So this is how your recursion is working, and how we are using pre-order to solve this problem. It's very simple. It's just that you need to understand for one condition. So like how we're going to return null, and when we're going to return the root, or when we're going to return left, and when we're going to return right. If you understood this for one particular condition, all the other conditions are very simple. And when you're coding it, all you need to do is code the exact same thing, right? Maybe recursion is hard, but when you have a solution in mind, and when you code the exact same thing, recursion will take care of the rest of the things, right? Because what is recursion doing? It's breaking a bigger problem into smaller and smaller problems, right? So whatever is in your mind, let's just say you code it. Like for me, whenever I found P, I'm returning P. When I found Q, I'm returning Q. Else I'm going towards the left, then I'm going towards the right, then I'm comparing left and right. This was a thought in my mind. and I just coded that. Recursion took care of the rest, right? This is how you solve any recursion problem or any problem that's based on trees. Okay, I hope you understood this. Please subscribe if you did. That'll be really good for me, and I'll see you on another video. Thank you.